Welcome back. Let's start my screen here. So there are a couple of major topics I want to try to cover today. One is eigenvalues and eigenvectors. Okay, and those of you who have studied linear algebra know what those are. And I will attempt to show you how to calculate eigenvalues and eigenvectors. Okay, and then say a few words about why they're important when it comes to machine learning. Okay. Then, as promised, I'm going to try to give a maybe 1 hour presentation on optimization. That was the other major topic that I was told that this class is supposed to cover, and I told the department I didn't think I had time, but I'm going to try to at least give you an overview of optimization so that when you encounter it in your machine learning classes, at least you'll know what they're talking about. Okay? And then there was one topic that I probably could have snuck in earlier when we were talking about regression. Excuse me. And that's the topic of logistic regression. It's not a very major topic, but at the end of the class, if we have time, we'll talk about logistic regression. Okay, but it's on my slides, so even if we don't have time to talk about it, you'll have it on the slides. Okay. All right, I want to start out by going over the solutions to assignment 12, and of course I need to upload my solutions. So let me do that so that you can have it and follow along. Okay. Let's make sure, there we go. And I have it on my, oops, wow, okay, forget that. 12, and I have the assignment 12 solution here. So I'm uploading it, and now you should be able to download it. You may have to refresh your browser, but let me check myself. Back up, data 220. Let's refresh the browser, and let's see what we got here. Yes, it's up there. Okay, so you should be able to download my solutions to assignment 12. And let me quickly go over my solutions. And once again, my solutions are basically one way to solve these problems. Like all math problems, there are many ways to solve them. And as long as you can explain what you did and you got the right answer, that's should be okay with us. Okay. All right, so let's take a look at, okay, here we are. Okay, here we are. Number 12, solutions. And I imported a bunch of stuff. Great. All right, so the first one was to find the least squares quadratic, which means degree 2 regression line through the following set of points. Okay, so these are the x's. Again, make an array out of them. That's always a good idea. Okay, let me clear all the outputs so I can be solving these as we go along. Okay, so all right. Okay, so we make an array out of the x's. We make an array out of the y's. Okay. Okay, I have to start up a kernel. Start the kernel. Okay, why isn't it restarting? I thought I had everything all set up to go, and then restart kernel. There it goes. All right, restart. Okay, now the kernel should be running. Okay, there we go. All right, so I make an array, a NumPy array out of the x's. Okay. There it goes. Wow, it took a while for that to do it. Okay, make a NumPy array out of the y's. Now I'm going to create the A matrix, and you know it has ones down the first column. Okay, and then the second column will be the x's. Okay, so the x values 11, 12, 13, etc. You see them coming down here. And because this is a quadratic, there's the third column will be x squared. Okay, so you can see here that I basically just squared each value, and you can see the third column is x squared. Okay, the right hand side b, well, that's just the y's, so I just said b gets the value y, and there it is. All right, then we grind through the matrix form of the normal equations, and pretty soon you'll be able to do this in your sleep. There's I guess I haven't been keeping this going, have I? Okay, there's a transpose. Okay, here we go, and we do all the various operations, and finally we come up with x hat. Okay, and x hat is these values. Okay, so those are the coefficients of our quadratic equation. Okay, and then I remember I had written this polynomial regression function that calculated everything with all the normal equations, the where all you had all those summations and so forth and so on, and sure enough we get the same answer. Okay, so I just wanted to double check. Okay, and then here we are plotting it all. Okay, and so you can see all the points, and here is the quadratic equation. Okay, degree 2 equation, and that is a parabola. Okay, and so if you then take these coefficients, you can plug them into our equation. There's y equals minus 20 whatever plus nearly 3x minus 0.046 x squared. Okay, so that is our quadratic equation. Okay. Now I pointed out that if you have n points, okay, this is problem 2, n points, and you did a least squares polynomial of degree n minus 1, okay, what you've actually calculated is an interpolation line. Okay, an interpolation line goes through all the points, so it's going to wind and twist and curve or do whatever it takes to go through all the points. Okay, it's pretty pretty exciting to see, I guess. Okay, so here I gave you 1, 2, 3, 4, 5 points. Therefore, you're going to generate a 4th degree regression polynomial. And so here we are with the x's and the y's, and I'm creating the A matrix. And so 1's down the first column. Here are the x's, x squared, x cubed, x to the 4th. Okay. Yeah. Now these 1's down the first column is really x to the 0th power. If you remember your math, high school math, any number to the 0th power is 1. And so this is really x to the 0th power, 1st power, 2nd power, 3rd power, 4th power. Okay, so it's actually very, very consistent. Okay. All right, and here's the b, which is the y's. Okay, and okay, here I just call solve instead of going through the matrix form of the normal equations, because it turns out we do have a square matrix. So you have 5 rows, 5 columns. Then we can just use solve, and we get the coefficients of the 4th degree polynomial. Okay, and if we plot it, okay, as I said, you end up with an interpolation line, and see it winds and twists to go through all the points. Okay, and this gets kind of dramatic if there are more points, right? If we had 10 points, you'd have a 9th degree polynomial, and you'll see it really, really twisting and turning to go through all the points. Okay? So this is an interpolation line. Okay. All right. Any questions so far? Okay.
Professor, I have doubt here.
Yeah.
How to decide the x mean and x max value here?
Okay, so oh, the min and max.
Yeah.
You know, I think I just played around with it until I got a graph that looked nice. So nothing magical here. I just, you know, wanted a graph that looked nice. So it turns out that these two values
Okay.
work. So there wasn't anything magical. I did just try a few numbers, and you know, with Python, it's so easy to do these things now. I mean, you didn't have to plot it by hand to see if it came out looking nice. Just play around with it until you get something that looked nice.
So,
Yeah.
Professor, in the same context, can we keep min and max as the endpoint of our x's, like -2 and +2?
So you want it min and max to be the min and max of the x's?
Yeah, so it will just stop at those points. So is it
Yeah,
okay?
yeah. Then your line would start here and end here.
Yeah, exactly.
Yeah, sure. I mean, as I said, I wanted it to look dramatic, so I wanted it to
Okay.
continue past it. But yeah, all you need is for the curve to go through all the points.
Okay.
Okay.
Thank you.
So again, whenever you have endpoints, if you calculate the polynomial regression curve of degree n minus 1, you'll end up with an interpolation line. Okay, and interpolation means it goes through the points. Okay. All right, here we go with a, well, hopefully you all figured out that this was a Markov chain. Now, I wanted to introduce you to Markov chains because later on you're going to be reading more or doing more things with what I know as Markov processes. And so at least you got introduced to Markov. Just as I introduced you to Bayes' theorem, when you do machine learning, you're going to encounter something called naive Bayes. And naive Bayes is an algorithm based on Bayes' theorem. So I kind of gave you the introduction to these, well, you got introduced to Thomas Bayes and to Mr. Markov. And then later on in your other classes, at least you will have heard of Bayes and Markov. Okay. Anyway, number 3A is, all right, so we start out with employees in that are ranked number 1, 2, and 3. And here you have the percentages. Okay. Of course, this should add up to 100% because there are only 4 ranks. And as a little thing on the side, we also have how much productivity loss employees in each of the ranks cause. And you can see that rank number 1 employees generate a lot of productivity loss, and then rank number 4, which it's at the top, very little. Okay. All right. So then we have a training course, and that is supposed to move employees from one rank to another. Hopefully, it moves them up and not down. And here is the prediction. It predicts what percentage of employees will move from one rank to another or stay in the same rank after each hourly training session. So, so after 1 hour, you would then apply this, and then after another hour, you would apply this again. So this is very similar to the problem where you have customers going to stores, and then at the end of the year, they a certain percentage of them will move from one store to the next. Okay, so it's that kind of problem. All right, so we're going to grind through this, iterate through this. Okay, we're constantly going to be multiplying a matrix P by the starting percentages, and then we will continue doing this until 2 consecutive hours have no change, up to 3 decimal places, right? Because I mean, you could go many, many more hours if you insist that the changes don't occur with many, many decimal places. But we're going to cut it off after 3 decimal places, okay? All right, so here's the initial percentages, okay? I just calculated the P matrix, okay? And for printing purposes only, I'm just going to print out 4 decimal places. This does not affect computation, by the way. It's only for printing, okay? All right, so we loop and loop and loop. Now notice how we test, okay? So this says we're going to subtract the new value of x, okay, subtract that from the previous value of x, and we're comparing the 2 vectors, okay, and for each or for all the components, we're checking to make sure to see if it's less than 10 to the minus 4th, okay, which means that will give us the 3 decimal places, okay, right? So, and then I print out each vector at the end of each hour, okay? All right, so we can watch it go, and what I had was 14 hours, okay? Maybe on your machine it was different, but it should be around 14 hours. And sure enough, okay, within 3 decimal places, the numbers are the same. Okay, well, here, slightly different, but it's still within 3 decimal places. And so training lasts 14 hours, okay? All right, any questions? Okay, and all right, so then after 14 hours, here are the percentages of employees in ranks 1, 2, 3, and 4. Okay, so we started out with only 10% of the employees were in 4 and 30% were in 1. And when we were after 14 hours of classes, we see that now only about 1/4 of the employees are in rank 1 and nearly 1/3 of them have moved up to rank 4. Okay, and then there were increases in the other ranks too. Okay. All right, now without iteration, okay, could we have calculated this new vector? Okay, and so what I showed you in class was that, yes, if we set it up as a system of equations, then we can apply our algorithms for solving that system of equations. Okay, so here again is, now remember we start out by subtracting the identity matrix here. Let me bring up those slides so we can remember what it is we're trying to do here. So, okay, wait, this is, make sure I'm in the right class. It's 220 lectures, and it was last week's slides. There we go. And okay, it's toward the end of the class, if I remember. Okay, there we go. And all right, so we're trying to compute this, and what I did was you subtract vector x from both sides, and so whoops, and so it, here's an x1 here, and you subtract that from 0.70 and you get minus 0.3, subtract x2 from both sides, and so it's subtracted from 0.8 and you get minus 0.02, and subtract x3 from both sides, and you end up with a minus 0.3. Okay, so basically what you end up doing is subtracting yeah, well, let's see what we end up doing here. Bring up the okay. So we end up basically subtracting 1 down the diagonal, and that's the identity matrix, is what we're subtracting from A. right? So here we basically subtracted 1 down the diagonal. Okay. All right, so that's what this is here. Okay. And then I inserted a new row, and you can see that this bottom row has all 1s. Okay. And then when I formed the B vector, the right-hand side, you notice the right-hand side here after doing the subtraction was all 0s, but here's all 0s and then a 1 here. Okay, so does anybody know why I did that? What was I trying to, what additional information was I adding to this problem? Okay. So if you do the multiplication of A times B,
It's like it should be like overall it should be like 100%. Is it what?
that's right. So it's saying that if you add up the percentages, okay, so you add up these percentages, it should add up to 1. So that is the additional information that I'm providing. Remember, when we tried to solve this, we ended up with a free variable, and we had to, and then we took advantage of the fact that when you add up the 3 of them, it had to be equal to 1. So that's what I put here, is that I added this extra row at the bottom, which if you multiply it by B, then it says that the 3 components or the 4 components of B have to add up to 1. And so here, the right-hand side after the subtraction is 0s, but then the last one is a 1. So that's additional information that I'm providing in order for us to get a solution. Okay. Okay. Well, now that I have an A matrix and a B vector, I again grind through the normal equation, grind, and then we end up with x hat, which is our solution. Okay, and we can verify that by multiplying p times x hat. And sure enough, p times x hat is equal to x. So there you go. Okay, and that equals what we had calculated earlier. Okay, by using all the iteration, we ended up with this final x, and it was this vector. And sure enough, if we compare, it's again the same value. Okay, with a little bit of round off there, of course. Okay, and if we add up the steady state vector, of course, it still adds up to 1, within a bit of round off there. Okay, and then I calculated. All right, we had from the original, we had the productivity loss. Okay, then with the new percentages, what was the loss? And so that's all that little bit of extra calculation was here, and we saw that we did get an 18.5% improvement. And so maybe it was worth 14 hours of training courses. Okay, hopefully that was spread over a week.
The improvement number, I think it's not right, because you have to subtract the 20.38 from the 25%, right?
Okay, so what did I do? Okay, so the new overall total was 20.38. So did I? Okay, so I subtracted. Okay, let's see. Plus back, and then okay, where? Oh, okay. So the improvement was the old total minus the new total divided by the old total, and so it was 18% better than the old total. Okay, so the old total was gosh, where was it? 25% total loss. And after the improvements, it was only 20% total loss. And so the improvement was around 18%. That's all that was. All right. So that was assignment 12. Just give you some practice generating a regression polynomial, and then you got to do a interpolation, and then we did a Markov chain. Okay. All right. There are no questions about this assignment, and that was your last assignment, by the way. You're not getting one tonight. Okay. All right. So this was last week, and all right. Let's talk about eigenvalues and eigenvectors. Okay. Basically, if you have a square matrix A, okay, then can you find vectors, okay, and corresponding scalars such that A times X, okay, is equal to the scalar times X. Okay? In other words, A times X is a scalar multiple of X. Okay? A times X, that product is a vector. And of course, a scalar times a vector is a vector. Okay. All right. So we have an eigenvalue, eigenvalue and an eigenvector. Okay. So let's take a look at an example. Here's A, and I'm going to claim that this is an eigenvector. Okay. Well, in order to substantiate that claim, I have to find the corresponding eigenvalue. And I'm going to say that, well, that's 2, because now if we do this multiplication, A times the eigenvector, that's going to give us this value, but that's 2 times the eigenvector. And so now we can claim that we have found an eigenvalue and its corresponding eigenvector. Okay. Now this is also an eigenvector. Okay, and here the eigenvalue is going to be -1. Okay, and sure enough, we do the multiplications. There's A times the eigenvector. That gives us this value, this vector here, and that's equal to -1 times the eigenvector. And so corresponding to this eigenvector is the eigenvalue -1. Okay. Well, that was a simple example. Let me show you a more interesting example. All right, here's A. Okay. Now, A will have 3 we'll be able to find 3 eigenvectors. Okay. And then each eigenvector, of course, has a corresponding eigenvalue. And so here are the 3 eigenvectors. Okay. And corresponding to each one is the eigenvalue. And if we multiply A times X, we get this. And if we multiply lambda times X, we get the same vector. And so there you have 3 eigenvalue eigenvector pairs. Okay. So this is an interesting property of square matrices. Okay. Now, if we look at the Markov steady state problem, okay, well, if you consider the steady state vector x bar to be an eigenvector, okay, remember that this is the steady state, okay, well, if you say that the eigenvalue is a 1, then all right, when you have a Markov steady state, the eigenvector is the steady state vector, and the eigenvalue is 1. So that there's another example of an eigenvalue eigenvector pair. Okay. All right. Well, now you're probably wondering, well, very interesting, but why bother? Okay. Well, eigenvalues and eigenvectors are used to decompose a matrix into its constituent parts in order to simplify complex operations. Okay, so I guess an analogy would be, all right, you're dealing with big scalar numbers, okay? And if you factor that number and work with each of the factors, then that's easier than working with the big scalar number. Okay, so I guess that is one way of viewing it. And so we decompose a matrix into eigenvalues and eigenvectors. That's known as eigen decomposition. Okay? Eigen is a German word meaning singular. Okay, you might find in the literature the word characteristic value and characteristic vector instead of eigenvalue, eigenvector. But I think the German word is more common. Okay. All right. Well, why would you want to do this? Why do you want to decompose a matrix? Okay. In your future classes, when you're doing machine learning, remember we did an operation called principal component analysis. Okay. Remember we had this iris data set and there were 4 features, and we wanted to do a plot, but plotting in 4 dimensions was too much for us. So we did a principal component analysis to reduce the 4 attributes down to 2, and then we were able to draw a plot. Okay, so PCA is going to be an important operation, because if your data has way too many attributes, you're not going to be able to do all the computations. Okay? Remember, the more computations you do, the more round-off error you accumulate. And so you're going to be doing PCA to reduce the number of attributes, the ones that are combine some attributes and so forth, and so you end up with a smaller set of attributes. Okay? All right, so eigen decomposition will be one of the operations that you'll be using to do PCA. Okay? If you're asked to do it by hand, of course, you saw that there are that TSNE function and the PCA function. Of course, Python gives you functions for doing this sort of thing, but if you're ever asked to do it by hand, you're going to be doing eigen decomposition. Okay. All right, and okay, I give you a bunch of links here if you really are interested at this stage to know why eigenvalues and eigenvectors are important in machine learning. There are a bunch of articles here. Okay. All right, now I want to show you the geometric interpretation of eigenvalues and eigenvectors. And so I have a function here that plots vectors, and it does it in up to 3 colors, blue, orange, and black. And so I've uploaded this code, and you're welcome to use it however you like. Okay, but here is a vector, 2, 1. Okay, so it's x is 2 and y is 1. So there's our vector x. Okay, now those of you who took linear algebra know that if you multiply a vector by a matrix, okay, so we're going to multiply x by this matrix. Okay, that's known as a linear transformation. Okay, so multiplying by x transforms the matrix to a different matrix. So if this was x, the original x, and we multiply x by a, we get this new matrix. We get this new vector, and so we've done a linear transformation or a linear mapping of x to ax. Okay? All right, so just a bit of terminology there. Okay. Now, what happens if we do this with eigenvalues and eigenvectors? Okay, so here is a vector of 1, 1. So there it is. Okay, and I'm going to multiply it by this matrix A. Okay, but it turns out that 1, 1 is an eigenvector, and the eigenvalue corresponding to this eigenvector is 6. Okay, so when I do the multiplication, okay, what happens is that AX, okay, which is this, okay, so here's the original vector, this orange thing, and AX is the entire line here, okay, but then AX is 6 times the vector, and so the geometric interpretation is that when you multiply, when you have an eigenvalue and an eigenvector, then all you've done when you multiply A times the eigenvector is you end up with a vector in the same direction that is the eigenvalue times longer. Okay, so here, this entire vector here, okay, is in the same direction as the original vector, but is 6 times longer, right? Because 6 was the eigenvalue. Okay? All right, and remember that A times X is equal to lambda times X. And so that's why we have this picture, okay? All right, so that is the geometric interpolation. Well, here's another example. Whoops, sorry. Just touch that mouse the wrong way and bad things happen. All right, so here we go. Here is A, okay? And I'm gonna say that this is an eigenvector, 1 minus 3. So there's this orange one here, 1 minus 3, okay? Unfortunately, the scales along the x-axis and the scale on the y-axis are different, and so this line didn't quite come out the way I would have wanted. But anyway, here's the eigenvector, and then the eigenvalue is 2, and so we end up with that A times the eigenvector is twice as long as the eigenvector on going in the same direction. Okay. All right, so there we go. Okay, so now you have an idea of what an eigenvalue and an eigenvector are, corresponding to a matrix, and of course a matrix can have more than one pair of these eigenvalue eigenvectors. Okay. All right, now for a given eigenvalue of a matrix, there are an infinite number of eigenvectors, right? Because you can multiply the vector by any real number. So let's say that, okay, we have this pair, lambda and the eigenvector, and I think, well, I just multiply x by 2, and this relationship will still hold. Or I can multiply x by 3, and this relationship will still hold. And so for a given eigenvalue, there are an infinite number of eigenvectors, okay? And so what we're going to do then is say, okay, let's normalize the eigenvectors so that there's only one of them, but it can go in either direction. But at least instead of having an infinite number of them, you can say, hey, I want the normalized eigenvector. And remember, a normalized vector has length 1. Okay. All right, so here we go again. All right, so here's a normalized eigenvector, and I put a little hat above it to indicate that it's normalized. The length of this thing should be 1. Okay, and then here is eigenvalue, and so all right, so if this is the original eigenvector, okay, so that's 1 minus 3, okay, this orange one here, starting from the origin, okay, and we saw earlier that if we multiply that by A, we get a vector that is twice as long, okay, and then we're gonna normalize the eigenvector vector x2, and that's this black one here, and its length is supposed to be 1. Okay. All right, so now you know that, all right, we can normalize the each of our eigenvectors. Okay, well, how do we compute these things? Okay, it's one thing for me to give you a matrix and then a square matrix, and I'll say, oh, here are eigenvalues, and then corresponding to each eigenvalue, there's an eigenvector, and yes, we can normalize the eigenvector. But then, well, how do we compute these things in the first place? Okay, well, I'm going to show you an algorithm. And I'm not going to try to prove why this algorithm works, okay? Because these things go really deep into advanced linear algebra, and I really don't want to stick our toes into that. So here is the algorithm, okay? So we have A, okay? And we're going to do QR factoring. So we're going to factor A into Q and R, okay? Oh, well. Okay, well, here's the theorem. Okay, if you have a matrix and it's upper triangular, then the elements along the diagonal are the eigenvalues. Okay, so if you have a 3 by 3 matrix and we convert that 3 by 3 matrix into upper triangular, then if you look along the diagonal, there'll be 3 eigenvalues. Okay, so that's the theory. Okay, and so given a square matrix, we want to convert it to upper triangular. Okay, and so well, here is the procedure. We factor A into Q and R. Okay, and we multiply R times Q. Now notice we do it in the opposite order. Okay, now we keep doing this. Okay. Until, and we keep multiplying R times Q, R times Q, R times Q until the product converges to upper triangular. Okay, so we're multiply R times Q, that gives us a new matrix. Okay, we factor that new matrix into Q and R, and then we do that multiplication again, R times Q. So R times Q, okay, factor it into Q and R times Q again, factor in the Q and R, and eventually the R times Q product will converge to an upper triangular matrix, okay? Now this may require a lot of computation, and so this could generate round-off errors, okay? And that is always going to be our nemesis when we do any sorts of iterative calculations. Especially with large matrices, is that you're doing a lot of multiplications and additions and so forth and so on, and you will get round-off errors. Okay, but hopefully with a small matrix we can get away with doing it this way. All right, so I have uploaded some code. Okay, here is a function that tests whether or not matrix that I'm calling RQ is upper triangular. And so basically I'm looking at the elements under the main diagonal to see if there's 0. And I'm not going to check for exact 0, because with round-off error, you probably will never achieve exact 0. So instead, I'm just going to say, well, is it close to 0? In other words, if all the elements are less than or equal to 0.0001, I'll say true. But you know, as I'm checking the elements under the main diagonal, if any one of them is greater than 0.001, I'm going to say no, it's not upper triangular. Okay. All right, so here's another function. Okay, factorize. Okay, you give it an A. So I'm going to start by calling RQ to be A. So RQ will start out being A. And I check, well, maybe we're lucky and RQ is already upper triangular. So the first thing I do is I check. okay? Otherwise, I'm going to do that multiplication, that repeated multiplication, and I'm going to put an upper limit on it, okay? Whenever you're hoping that something will converge and you're iteratively doing multiplications or whatever and hoping that an answer converges, you better put an upper limit on it because maybe it doesn't converge. It could be that it was never meant to converge in the first place, or because of round-off errors, even though theoretically it should have converged, it didn't. So you always put an upper limit on it. So I'd say, okay, well, do this 100 times. Okay. All right. So here I am factoring my matrix into Q and R. Okay. And then the new RQ is going to be R times Q. Okay. And so then and then I loop again and check, okay, is the new value of RQ upper triangular? If not, I do this again. And so I do this hopefully less than 100 times. And then we will finally get RQ to be upper triangular. Okay, so, all right, so that's what we have here. Okay. Okay, oops, what happened? All right, so now finding the eigenvalues, okay? Given a square matrix A, and I really should check to see if it's square, but I get its size, okay? And I initialize eigenvalues to be all 0, just to start out. Okay, I factorize A. Now what did factorize return? It returned the size of the matrix and RQ. That's what it returned. Okay, so I factorize it. Okay, and and then of course factorizing also then when we come back with RQ, we assume RQ is upper triangular. Right. All right. So then that means that the eigenvalues are along the main diagonal of RQ. Okay, which is matrix A converted through our iterative process into upper triangular. Okay, so now we have the eigenvalues along the diagonal. Okay, so this guy here returns n, the size of the A, the upper triangular matrix in case you want to do something with it, and then the eigenvalues. So this function returns 3 items, which you have to unpack when you get back the return values. All right, so those are 3 functions that I wrote, and let's give it a try. Okay, so here is a matrix, and I call my find eigenvalues, and if I want to print out the okay, here I actually are printing out the iterations. Okay, did I actually have that there? Okay. Oh yeah. Okay. See, my factorize function prints out all the iterations. Okay, so you can see that RQ is not upper triangular until we get into the later iterations. Okay, finally we do manage RQ being upper triangular, and therefore the eigenvalues are 6 and 2. Okay. All right. So now we've calculated the eigenvalues. What are the corresponding eigenvectors? Okay. Well, we know this is true, and so therefore we can solve this system of equations. Okay. Right, so, all right, so here is our original matrix here, A, and one of the eigenvalues that we had calculated was 6, right? Let's see. Yeah, we got 6 here. So, okay, well, we know that A times X has to equal 6 times X, right? And so this is a system of equations. And what we're going to do is we're going to subtract 6X from both sides, okay? And so we subtract 6 from the 5 here and 6 from the 3 here, and we get this. And so what we actually did was AX minus 6 times the identity matrix times X. Okay, and that gives us this. Okay, and then on the right hand side, you can, sorry, on the right hand side, you can actually see me doing these operations. Okay, and we end up with B here of 0, 0, and we try to do a solve, and we get 0, 0 as the eigenvector. Okay, well, that's not good. Okay, it's not meaningful. And why is that? Well, quite often A times the eigenvalue times I, which is the operation that we had to do here. Okay, the result of that is often can be singular, and well, it turns out to be singular because remember I said that there are an infinite number of eigenvectors for a given eigenvalue, and so solve cannot handle that. Okay, so one way to do it is to force one of the components of X to be some value. Okay, so X has 2 components, so we'll make one of them a 1. Okay, just do that. And so now our equations, instead of just being this, is now it looks like this. Okay. Okay, well now we cannot use solve because we have 3 equations and 2 variables, and solve only works with square matrices, and so we have to use the normal form of the or the matrix form of the normal equations, and so we grind through this again, and so go through this, and what we finally end up with is this eigenvector. Okay. So X hat then is we get 1, 1, and then we normalize it, and so after normalizing 1, 1, we get this is the normalized eigenvector corresponding to the eigenvalue of 6. Okay, so now you know how to calculate the eigenvalues, and for each eigenvalue, you can calculate the normalized eigenvector. All right, so it takes a bit of work. Okay, so then of course, well, okay, so here I've actually written some Python functions that go through all these steps. So let's take a quick look at them. All right. Okay, so eigenfactorization. Okay, there's checking upper triangular, factorizing, finding the eigenvalues, which of course is just reading off the diagonals of the upper triangular matrix, and then finding the eigenvector, which is going to, well, here it looks like I'm using QR factorization to actually solve that system. And then that gives us the eigenvectors. Okay, so that is a couple of functions I'm providing, and then okay, well, I didn't show you any of these. Okay, so here eigenfactorization. Okay, let's run this and see what we have here. Okay. All right, we have to start the kernel. Start kernel and run all cells. Okay, there we go. Okay, so basically this is the test program, and you can see that I'm going through those iterations as you saw on the slides, and then Okay, I do several different matrices. Okay, so this is basically a test program for the functions that I wrote in eigenfactorization. Okay, and test eigenfactorization 2. Okay, let's see what happens here. Okay, restart kernel and run all cells. Okay, this one I think I deliberately had some. Okay, let's see. Okay, okay. Okay, this is given the eigen values, I'm calculating the eigenvectors. Okay, so here we see the that one corresponding to 6, and then what was corresponding to the other eigenvalue of 2. Oh dear! So here we ended up with singularity. Okay, and so then I had to force one of the values to 1. Okay, so you see that here. If I'm not going to run from select cell all below, and finally, well, oh, okay, we got, okay, we did get the eigenvector corresponding to eigenvalue 2. Okay, and then I do another one where it's a 3 by 3, and let's see what happens here. Okay, we do manage to calculate some eigenvectors. Okay. All right, so just some example notebooks that make use of our function to calculate eigenvalues and eigenvectors. Okay. Now, after showing you all this, you know, all that work we had to do, of course, now I'm going to say that there is a Python function that does all the work, and it's the EIG function. Okay, and basically you give it a square matrix, and you call EIG, and it returns the eigenvalues and eigenvectors, just like that. Okay, but now you have an idea of what it's doing under the covers. Okay, but it's going to do it in a much more efficient way than, see, we did all the work using more Python functions. Now EIG was probably written in C, and so it's going to do it a lot faster than we could have done it by writing more Python functions. Okay. All right, that was factorization 3. So let's see what I have here. And all right, so here I'm calling find eigenvalues, and that okay. Let's see. I think I'm comparing what I wrote against the EIG function. Okay, so all right, well, let's take a look at the EIG function. Okay, so here is our original matrix. Okay, and okay, we do the calculations with you know, converting the matrix alpha triangular. We pick off the eigenvalues. We compute the eigenvectors. Okay, and then we compute the norms of them. Okay, now if we use EIG instead, we get the same results. Okay, the same results. Okay, the eigenvalues are 6 and 2, and we get the eigenvectors, which can then normalize, and we end up with the same values, but with a lot less work. Okay, and because all we had to do was call the EIG function. Okay, so let's take a look at that notebook. That was eigen number 3. And okay, this is okay, you can see where this is coming from. Okay, and I'm importing the functions that I showed you earlier, where I did all the work the hard way. Okay, and then verify is doing the multiplication is multiplying A times the eigenvector, and then it's multiplying lambda, the eigenvalue, times the eigenvector, and they should be the same, of course. All right, so then this is the test program, and it calls my functions, and then test EIG basically just calls the EIG built-in function, okay? All right, so let's run this. Now, I deliberately put in some bad matrices here, and so we're gonna get some runtime errors. Okay, so let's kernel, restart kernel, and run all cells. Okay, so there it goes. And okay, so for this matrix, I start out by giving you some symmetric matrices. Symmetric matrices have certain properties, but they're called symmetric because if you look on either side of the diagonal, it's a mirror of each other. So here's the diagonal, and you see there's 2 and a 2 on both sides. Okay, so okay, here I am doing it the hard way, and we get these normalized eigenvectors, and here I am calling EIG, and we should be getting the same. Okay. Well, actually, what I'm doing here is demonstrating that if you multiply it, that you will get the same values. So here we have 2 eigenvalues, and so this is using a -6, and this is using -1, and sure enough, A times V is equal to lambda times V in both cases. And the same thing here when we use EIG. Okay, and then here's another symmetric matrix. If you look along the diagonal on either side, here's a 3 and a 3, and a 0 and a 0, and so forth, a 4 and a 4. Okay, we generate the upper triangular. Oh, okay. Well, I should point out that when you start out with a symmetric matrix, when you convert it to upper triangular, that actually end up with a diagonal matrix. You have non-zero entries along the diagonal, okay, and 0 elsewhere. And so here is another symmetric matrix, and you can see that not only are these the eigenvalues, but along the diagonal, but everything else is 0. Okay. All right. So here are the eigenvalues. The columns here are the eigenvectors, and then we verify that the norm of each one is 1. See, the norm of this one, okay, is 1. The norm of the second one is 1. So that demonstrates that these are the normalized eigenvectors. And then when we do the multiplications, they turn out to be the same. And then we get the same thing here with calling the EIG function. Okay. All right, so another symmetric matrix. And then eventually I have okay, this one's not symmetric. Okay, so here, well, I think this is the example I had on the slides. Okay, and then here's a test EIG. Okay, here's another one. This one is not symmetric. And okay, so we go through several of these. And then later on, I do have ones that cause problems. Okay, well, this one, you need a pretty high tolerance, okay, in order to decide that this is actually upper triangular. And you see it took 42 iterations before we could safely decide that this was upper triangular, okay? And okay, and then EIG, of course, gives us the same values, eigenvalues, eigenvectors, okay? All right, so, okay, so go ahead and take a look at these, and I have some notes here that you have to set these up a certain way, otherwise we get failures. And so if we write our own code to do all the iterations, we can get into trouble. Whereas the EIG function, obviously whoever wrote it knew what he was doing, or he or she knew what they were doing, and accounted for these various problems. Okay. All right. So here we're starting to get into problems here. Okay. All right. That is the EIG function. So now you know what eigenvalues and eigenvectors are, and you can calculate them just by calling EIG. Okay. But you can also calculate them using all the various matrix operations that I showed you, okay, which can take a while. All right, so, okay, and then I have a program here that tests, okay. So this is testing, doing it the hard way. This is testing using just the EIG function, and you can see that calling EIG is, at least with this example, 50 times faster than doing it with all the Python matrix operations. Okay, so I would assume that all the calculations inside the EIG function is done using code that was written in C, which generates a very, very fast compiled code, as opposed to Python, which is, well, it's not generating fast code. Okay. All right. Any questions about eigenvalues and eigenvectors? I'm going to show you one more thing that we can do with eigenvalues and eigenvectors, and then we'll take our break. Okay. All right, matrix powers. Okay, now you've seen earlier that we had done things such as the Markov chain problem, where we had to calculate some matrix to the nth power. Okay, and again, that can be very slow, and because of all the multiplications and additions, when you're calculating all those dot products, you run the risk of round-off errors. Okay. And so remember this first Markov chain problem that we saw last week, where it was the probability of switching from one store to the next. We ended up doing 22 iterations before we reach the steady state. Okay. Now it turns out that we can use eigenvalues and eigenvectors to calculate this without needing to calculate p to the 22nd power. So remember, I said early on that by decomposing a matrix into its eigenvalues and eigenvectors, certain operations, certain matrix operations can be done more efficiently and with fewer calculations that might generate round-off errors. Okay. All right, so let's see how we do that. Okay, so first we compute the eigenvalues of p. Okay, p being our probability matrix here, and the corresponding eigenvectors. Okay, so here's p, and all right, I'm actually calling my routine that will calculate the eigenvalues. Okay, so here we got 1.65 and 0.55. Okay, and then I calculate the eigenvectors. Okay, and I don't bother to normalize them. Okay, and so here are the eigenvectors. Okay, each of the columns. Okay, and what we want to do is to represent the initial state vector. Okay, these were the initial percentages of people in the various stores or in our no store, and we want to represent the initial state vector as a linear combination of the eigenvectors. So they want this to be x1, x2, and x3 are the eigenvectors, and so to get a linear combination, we have to compute the coefficients. Okay, Well, we know how to do that because we can call solve. Okay, so if we have the eigenvectors, okay, so this is the matrix of the eigenvectors. Okay, that was this matrix here, where the columns were the eigenvectors. Okay, and we have the right-hand side, which we're going to use as the initial x vector. Okay, well then we get the A correspondence, the A coefficients. Okay, so here's A sub 1, A sub 2, and A sub 3. Okay. All right. So all right. This is just a check to make sure that, okay, let's see, what are we doing here? Where we're multiplying, or calculating T, which is the coefficients times the eigenvectors. So here I am doing the calculations, and sure enough, they match. Okay, so that tells us that we did indeed generate the linear combination of the eigenvectors. Okay, so all right, so great. Now what? Okay, well, okay, here's the magical formula, right? Remember that steady state x was p to the 22nd times the initial vector. Okay, well, to calculate that, we can do it this way instead. Okay, we can calculate the 22nd power of the individual eigenvalues, okay, and multiply that by the eigen vectors. Okay, so we can calculate this pretty easily. We know we're not going to multiply this number by itself 22 times. We're going to, the way Python does those kinds of things is with logarithms and so forth. And so we have a lot less chance of accumulating round off errors by raising each of the eigenvalues, which each of them is a scalar, to the 22nd power, as opposed to multiplying this entire matrix by itself 22 times. Okay. All right, so here I am doing that, and you know that in Python, star is raising to a power. Okay, and so we end up with this value, which of course is what we had calculated initially. Okay. So here we did manage to calculate x bar without actually having to multiply or raise p to the 22nd power. Okay. Now, okay, here's a little side note here. So what I did was I wrote out this expression using the sigma notation. Okay, and so a to the n, okay, here n was 22, is the sum of each of these, where the lambdas and the x's are the eigenvalues and corresponding eigenvectors. Okay, now if n is large, okay, let's say this is a pretty big number, then and then it turns out that you arrange this equation so that the first term has the largest eigenvalue. Okay, I mean you can arrange these terms in any order. So if you have it so that the largest eigenvalue happens to be the first is in the first term, okay, and n is large, that means that an approximation of this entire expression is just the first term, right? Because it's going to dominate the rest of the terms. And so if you want a quick and dirty approximation, you can just say that, well, if n is large and lambda sub 1 happens to be the first or happens to be the largest lambda, then you can use this approximation. Okay. So you know, if you don't need an exact answer, then this is like a very quick way of getting X bar. Okay. All right, so this is just a clue as to how eigen decomposition can make matrix operations easier. Okay. All right. This is from assignment 12. This was the percentage of workers moving from one rank to another. Okay, and so matrix power is my notebook. Let's take a look at matrix power. Where's my notebook? Okay, matrix power. Okay. All right, so it does what I showed you. Okay, so it raises each of the eigenvalues to the nth power and multiplies that by the corresponding eigenvector. Okay, and so if we use this function to calculate, we should get the same answer as the way we did it the other way in assignment number in assignment 12. Okay, so okay, well, here's matrix powers, and okay, so that should have given us the same answer. Let's do a quick verification of that. Okay, assignment 12, and okay, we got 24.7, 24.1, and 24.7, 24.1. 19.2 and 32, 19.2 and 32. Yeah, all right. So this is a much faster and more accurate way of doing that calculation. Okay. All right. I know this was a crash course in eigenvalues and eigenvectors, and you just have to believe me that in your machine learning classes, when you're doing principal component analysis, you will be using eigenvalues and eigenvectors, okay? Unless the instructor of that class says, oh, just call this function, and then you don't have to worry about exactly what's going on. But I think it's important to know what's going on, okay? All right, let's take a break. And it's 7:20. Why don't we take a break until 7:35, okay? And then we'll come back and I will give you another crash course, this time a crash course in optimization, okay? So we're gonna break until 7:35 and my cat is threatening to walk on the keyboard. Okay, any questions? If not, okay, either I put you all to sleep or you're ready to go into break. And whoops, and I will then temporarily pause the recording. All right, we're recording again. I'm going to share my screen again. Okay, so as I said, we're going to embark on a new topic called optimization. And I saw this on the internet, so it must be true, that the 3 pillars that support data science are, as you see here, statistics, which probability is a part, linear algebra, and we're pretty much finishing off our unit on linear algebra, and optimization, which I'm going to talk about next. Okay, so what does it mean to have optimization? Okay, so there are 3 components of an optimization problem. There's what's known as the objective function, okay, which I'm calling F here in this example, and it can have 1 or more variables. So it could be F with just 1 a variable, independent variable x, or it can have two independent variables, x and y, or three, x, y, z, etc. Okay. And those independent variables are known as the decision variables, okay? And the decision variables may have constraints. So you're saying, well, I'm going to limit the x values to this range and limit the y values to that range and so forth. And there may not actually be any constraints, which means that x and y and z can have any value, okay? So now, so the optimization problem has those three components, and the problem is you want to find values of the decision variables that maximize or minimize the value of the objective function. Okay, so that's the optimization, finding the maximum or finding the minimum. Okay, now if you have a maximization problem, meaning you've got this function f and you're trying to find values of x and y that maximizes the value of f, okay, f being some function. If you have a maximization problem, you can convert that to a minimization problem by taking the negative of f, okay? So the maximum of f will be the minimum of negative f, and vice versa, okay? If you have a minimization problem, you can convert it to a maximization problem, okay? All right, so optimization means finding either the minimum or the maximum, depending on the problem, okay? All right, now, why do we bother with this? Okay, so in machine learning, you want to create a model, right, that performs well and gives you accurate predictions of some parameter for a given data set, right? So that was the whole purpose of machine learning was to do these predictions, okay? So if you have a cost function, okay, which is the difference between the true value of the estimated parameter and the predicted value. Okay, remember when we were doing my machine learning examples, you had the training set and then you had the test set, and after you train the model, we ran the test set through it. Now the test set was made up of x values and y values, but we used the model given the x values to predict the y values. Okay, so the cost function then is the difference between the actual y values and the predicted y values. Okay, so that's what's known as a cost function. Now, of course, in machine learning, we want to minimize the cost function. Okay, so given a model and then the cost function, which is the difference between the predictions and the actuals, you want to minimize the cost function. And how are you going to do that? Well, your model has these parameters that define the model. Now, these are the hyperparameters. And so you want to adjust the hyperparameters. Yeah, you want to adjust your model in order to minimize the cost function, right? You want your model to predict as well as possible. And in other words, you want to minimize the difference between the predicted values and the actual values. And if that difference is the cost function, the optimization problem is how can we adjust the hyperparameters of the model in order to minimize the cost function. Okay, so if you go back to what I have here, if f is the cost function and the hyperparameters are the decision variables, okay, you're trying to find the values of hyperparameters that will minimize the cost function. Okay, so that's where optimization comes in to machine learning. Okay. All right. Any questions so far on why we're doing any of this? Okay. All right. So let's take a look at linear regression. Okay. So remember, the model was the regression line. Okay. So here are a bunch of points here, and here's the the regression line. Remember, we calculated the regression line to minimize the sum of the squares of the difference between the predicted value, which is on the line, and the actual value. Okay, and so you can see here. So the variables then are the coefficients of the regression line, right? We want to adjust the coefficients, which then adjust this line. Okay. Now we have no constraints because, well, we don't need constraints for this problem. Now the objective function is we want to minimize the difference between the actual y values and the let's see. Well, okay, you see here we are summing up the squares here. Okay, so okay, the a's are the coefficients of the regression line. Okay, so there's a0, and then the summations are the remaining coefficients multiplied by the x values. Okay, and we're subtracting the difference between what the regression line predicts and the actual y value, and we're squaring that difference. Okay, so that's the function we want to minimize. Okay, so we're trying to find these coefficients which define the line to best fit the data. So this is looking at linear regression as an optimization problem. Okay, so this is the statistical model. Okay, what we had been doing earlier, and then this is the optimization model where we're trying to minimize this function. Okay. All right, so this is a simple example of minimizing a function. Okay, we're trying to minimize the sum of the squares of the differences between the predicted values and the actual values. And so we're trying to find the coefficients, these a0s in the regression equation that will minimize that function. Okay, this is the cost function. Okay. All right, so any questions? Okay. Now there are various algorithms for doing this. So if we are going to try to solve linear regression by treating it as an optimization problem. Okay, I'm not saying that's the best way to do it, but you know, I wanted to start out with a simple example. Okay, well, there are various algorithms for doing this, and a popular one is called Nelder-Mead. Okay, and basically it says that, okay, if we have a function that we're trying to find the minimum. Okay, we just start out with some point x sub 0 and calculate the value of the function at that point. Okay, and then we move a certain distance, okay, to a second point x sub 1, and then calculate the value of the function. And it turns out that, let's say we're trying to find the minimum, we're minimizing. If we move to the next point, and sure enough, the function is less at that point, then that says, hey, we're going in the right direction. And so you go in the same direction to x2, and then do a test to see if the value of the function has decreased. Okay, so this distance that you move is called the learning rate. Okay? And you can actually increase the learning rate. Let's say that you're going in a certain direction, and by golly, you know, the value of the function is getting less and less and less each time. You can get brave and increase the distance that you move. Okay, and in fact, as long as you're going in the right direction, you keep increasing the distance that you move, you know, to speed up getting to the minimum point. Okay. Now, at some point, you may overshoot the minimum, right? And so, gosh, we moved from this point to that point, and at the other point, the value of the function actually increased. Okay, so then you backtrack and go the other way, right? And there you may say, okay, well, we went too far, so let's go back, but let's not go back the same distance that that got us there. Let's maybe cut that distance in half, right? Because if you go back the same distance, you end up at the same point. So you so you cut the distance in half, and then again start moving in this other direction to see if the value of the function is getting smaller and smaller. And again, you may overshoot and you change direction again. And each time you change direction, you decrease the learning rate, you decrease the amount that you travel. And so the idea is that you are converging upon that value of x that gives you the minimum value of the function. Okay, so that is the algorithm, and it probably is easier to show than try to explain. So here's the problem. Okay. Well, here's the learning rate. Okay, so if you're doing a big learning rate, you can see that you're taking big steps, and if you're doing a small learning rate, then you're taking small steps. Okay, so here we're obviously trying to find the minimum. I'm not sure what you're trying to find here, but you can see that the learning rate is a big here and small here. Okay, now here's the problem with the Noether-Mead algorithm is that, well, you could have what are known as local minima. Okay, so here's a minimum, but it isn't the global minimum, which is the absolute smallest value. And by using this algorithm, you could end up here, right? Move up, overshot, come back around, and you end up here instead of finding the global minimum. So that is a problem with this algorithm. Okay. Whoops, what happened here? Okay, I got a blank slide in there somehow. Hang on. Do I really have a blank slide? No. Oh. Okay, I don't know where that came from. But okay, all right, so now you know about a big learning rate, a small learning rate, and possibility of ending up at a local minimum, but not the global minimum. Okay, so, all right, so I want to show you an animation of all this. And there's a wonderful website that has animated all these algorithms. So let's go there. Let's see if I can find it again. Okay, let's see. This is not the right. I should have opened this during the, okay, here we go. This is the right one. Okay, it was, oh, come on. Oh, here we are, here we are. Okay, so, all right, so here is a function, and okay, so here you can actually set the expansion rate. So as long as you're going in the right direction, you can increase the learning rate. Okay, and then when you find out you've overshot and you have to go back the other way, you can contract. Okay, so here you can see that. Okay, we start here. Okay, the steps get bigger and bigger, and then we overshoot, and you can see that then we decrease the learning rate. Okay, now you can see here that if I started here, okay, we end up at a local minimum, and we don't actually find the global minimum. Okay, so that's a problem with this algorithm. So this blue line here is this function. Okay, and we're using this algorithm to optimize the function by looking for its minimum. Okay, so there it goes. And we can adjust the various scale. Okay, let's really go here, and then we'll make the contraction rate that. Okay, then we'll see. Okay, big steps. Okay, and then so you can play around with this. Okay. All right, that is the Melder-Mead algorithm. I'm going to show you some Python code and before we're done. Okay, so all right, now gradients. Okay, now this gets into some pretty advanced, well, not advanced, say second-year calculus. But don't worry, I'm not going to sick the calculus on you other than to show you this. Okay, so another popular class of optimization algorithms is uses gradients. Okay, and in fact, if you're doing minimization problems, then the algorithms are gradient descent because you're descending down to find the minimum. Okay. Now, for all of you math majors, what is a gradient? Well, if you're a math major, I don't have to tell you what a gradient is. So we have a function that is made up of, that has one or more independent variables. And we use the gradient operator, okay, that is called del or nabla, okay? And del of this function is this vector. Okay, so the del operator always for a function gives you a vector, and if it's a function of say two variables, then this vector will have two entries, and if it's three variables, three entries, and each entry of this vector is the partial derivative of the function relative to each of the variables. All right, so that's all I'm going to say that requires advanced calculus. Okay, but this was just to remind all the math majors what a gradient is. Okay, now intuitively, a gradient says that if you're at a given point, okay, then the vector tells you which direction to go to increase or decrease the value of f most rapidly. Okay, so it's the ideal direction to go. Okay, so if it's a well, in the example that you saw, it was a function of just one variable x. Okay, so that wasn't so interesting because you only go in one direction. Now, in the case of a function of two variables, then it's a two-dimensional object, and if you're sitting on the surface of this object, you have a x value and a y value, then the del will tell you which direction to go. That will give you the highest ascent if it's a maximization problem, or the lowest descent, or I guess the steepest ascent or the steepest descent. Okay, so that's very useful, right? You're standing on this three-dimensional surface, and let's say it's a maximization problem. Well, which direction should you go that will give you the steepest ascent? Well, this del operator will tell you. Okay. All right. So so then again, like the example that we saw earlier, once you know which direction to go, you then have a learning rate, and you go a certain distance in that direction, and then you check. Okay. Now that I'm at this new spot, have I gone? Is the function greater than it was at the previous spot? Okay, and if so, then you are going in the right direction, and you look at the del again, and that will tell you, okay, from this second spot, which direction should you go again to get the steepest ascent. Okay, And if you overshoot the maximum, then you turn around and go in the other direction, maybe with a smaller, well, you do want a smaller a learning rate. Okay, so it's just like the example that I showed you earlier, except now we use gradients because we're talking about a higher higher degree. More than just one independent variable. Okay. All right. So let's take a look at this. Okay. So here. Okay. Here's a three-dimensional shape here. Okay. So this is a function in two variables, x and y, and so you're sitting here, and the del will tell you which direction to go that will have the steepest slope, okay, the steepest ascent, okay. And if you just look at the x and y values, basically that says that, okay, if you're here, okay, at this xy value, you want to go to this other xy value, okay? And if you look at the three-dimensional image, then you're climbing this hill in the direction of the steepest ascent, okay? And of course, if it's a minimization problem, then you're going down the hill with the steepest descent, okay? This one's a picture of a maximization problem, okay? All right, so gradient descent is for going down to look for a minimum. Okay. Now again, there are some very nice animations. Okay, so let's go back to that web page. Okay, and okay, so here. Okay, so this is doing a gradient descent. So we're going to assume that that's our maximum. Well, is the minimum or maximum? I forget which way. It doesn't really matter. I mean, the algorithm's the same. Okay, I guess look at the contour plot. Okay, it looks like this is probably a maximum here. Okay, so we can start anywhere here. And you can see the algorithm working. Now, this is in 3 dimensions, and so there are 3 points, okay? Okay, so you see it walking around. Oh, change direction, no, going that direction, go that way. And there we go. And again, we have the expansion rate and the contraction rate. So let's go nuts here. Okay. Now the problem with a very high expansion rate is that you can overshoot your goal and not find it. Okay. Let's see if I can force that to happen. Okay, this is crazy here. Okay, well, it starts changing direction pretty quickly, and so oh, look at it go. Okay, so you can see it oscillates around the maximum point. Okay, and if you make let's put this back down to 2, and if you make the contraction rate too small, then it may take forever to get there, because let's see. Maybe it goes the other way. Okay, yeah. See, it changes direction. It just takes longer to get to. Okay, come on, we're almost there. Okay, you see the loss is getting smaller and smaller here. Oh man, it's going to iterate a lot. Okay, so okay, there's that example. Let's see what else we have here. Oh, okay. Okay, this is the one that has several. Okay, he's talking about descent. So I guess these are minimization problems. Hang on, make sure. Okay, that was Noether-Mead. This is, okay. Oh, okay. Well, this is also Noether-Mead, sorry. Okay, now here's gradient descent. Okay, so here, gradient descent. Now that uses that a del operator to tell us which direction to go. And so let's see how this one works, okay? And then there's the learning rate. All right, so let's start here. Oh, going that direction. Okay, so it zeroes in pretty quickly because of the del operator tells us exactly which direction to go. And so there's a lot less trial and error here. So there's a lot of trial and error in here. Okay. Oh, it went the wrong way. Let's go the other way. You know, and so, okay. All right, so here, okay, let's start here instead. Okay, well, that's just gonna take us right there. Okay. Let's see what happens when we increase the learning rate to here. Whoa, okay, see what happens when the learning rate is too high? You just overshoot. Whoops, okay. So let's not do that. Okay? And if it's very low, okay, it just takes longer. Okay. So when you code up these algorithms, then you have to decide what should the learning rate be. And if you're doing a Noether-Mead, what's the expansion rate, what's the contraction rate, and so forth. Okay. Yeah, this one's going to take a while. So let's put back to on here, and we get there a lot quicker. Okay, let's start here. Okay. All right. Now there are variants of this algorithm. Okay, here's a. Okay, you can see that it is showing off some of the math that it's doing in those yellow arrows. And I'm not even sure where the minimum is in this. I guess it seems to be heading there. Okay, let's try starting here. Whoa. Okay, so you can see that this algorithm has some features that allow it to zero in quicker. Okay. All right. This is a really fun example. Okay, so what he's got is a table of the distances between the cities. Okay. And then he randomizes the locations of these cities, and these various algorithms try to find an arrangement of these cities that will minimize the error between the predicted distances and the actual distances. Okay, so here let's use Noether-Mead. Okay, and randomize. And it turns out Noether-Mead is a very bad algorithm. So here you can see that it's trying to find the ideal positions of these cities so that the distances between them is the closest possible match to the actual distances that's in some table. Okay, and you can see that Noether-Mead has no idea. Well, it's trying very, very hard, and you can see it's going to be a lot of iterations. Okay, so we won't use Noether-Mead. Okay, now how about we use gradient descent? Okay, wow. Okay, all right. See, it put all the cities in the right place, and so this arrangement of cities then minimizes the errors in the distances. Now that's gradient descent. Okay, now there is a variation of gradient descent, and oh wow, that one seems to have worked a lot faster. Okay, but you can see there was some zigzagging here. And then the last one, conjugate gradient, seems to be the fastest. Just zip and everything's there. Okay. Let's really go whole hog here. How about 25 cities? Boy, it put those in place really quickly. Okay. Now, how about that one? You can see that looks like Vancouver. They had a bit of trouble placing Vancouver. It looks like maybe this is the path to New York. Okay, let's do that one again. Yeah, there's some oscillations toward the end there. Okay, gradient descent. Okay, looks like it made it, but it took a while. Okay, and we're not even going to think that Notre-Meade has any hope of doing this. Yeah, okay, so forget Notre-Meade for this one. Okay. All right, so these are examples of doing optimization. Okay. All right, now I said I was going to show you some code. Okay. And okay, Python. All right, now there are several libraries here. There's now to do least squares optimization. That was the first example that I showed you, right? We're going to optimize this least squares function, okay? And there is actually a library that does that, scipy.optimize least squares, okay? There's also a global optimization problem that I'm going to show you, and that is given a function that has multiple minima, okay, can we find the global one? And yes, indeed, there is a Python function that does that. Okay, so okay, so all right, so let's take a look at these. And I did not write these programs from scratch. I stole the programs from this website, and then I tried to clean them up a little bit to make the programs a little bit better. Okay, so let's actually look at the programs. Okay. Oh, somebody sent me a message. It was from me. Examples of applications of which, okay, well, I just showed you some examples. Okay. All right, let's take a look.
My question is more related to like real world application of it. So cities are example, what kind of applications uses this kind of implementation?
Okay, well, as I said, in machine learning, you're coming with a model, and you want that model to give the most accurate predictions as possible. And so the cost function is a function that gives you the differences between the actual values and the predictions. Then you're going to use some optimization technique to try to minimize that cost function. Okay, remember a machine learning model has these hyperparameters that basically define the model, and you're trying to come up with the parameters that give you the model that will have a cost function. Well, you're going to minimize the cost function by coming up with a set of hyperparameters that will that you can use to define your machine learning model. Okay, so that is how optimization is used in machine learning. Okay, it's to enable you, or is a way for you to construct a model with the proper set of hyperparameters. Okay, those are the decision variables that minimizes the cost function. Okay, so does that make sense?
Yes, got it. Thank you.
I mean, as I said, this is such a brief introduction. I mean, I could have spent at least an entire lecture on this, and then I would have given you a homework assignment where you actually had to do something like this. There are no assignments tonight, so all I'm going to do is give you an introduction to this. Okay, I was going to actually give you some code And since I didn't write these, or at least not from scratch, I probably will not be able to explain exactly what is going on in all this code. So let me close off everything, and then I'll launch. Okay, so here is least squares optimization. Okay, and all right, so you can see that we're creating a model here, and there's a function, okay, where we're using the model, and that there's a definition here. Now, let me run this, and you'll see what's going on. Okay, so kernel, restart kernel, and run all cells. There we go. Okay, so basically, this is using optimization to plot the least squares polynomial among these points here. Okay? And so the model here had to figure out, okay, here are the coefficients of the polynomial. Okay, so all this was to calculate the okay, so here is least squares. Okay, so this is the optimization function, okay, coming out of scipy.optimize. So this is basically the example that I showed you early on, okay, where we looked at a regression problem as an optimization problem. Now here, the regression was a straight line, but you saw that in the Python example, we actually created a curve. Okay? So that was that, and as I said, I didn't write that, so I cannot tell you exactly what each line is doing. Okay. Now the other one is more dramatic. Okay. Okay. So here there is a function called egg carton. And you'll see why in a second why it's called the egg carton function, because when you plot it, it looks like an egg carton. Okay, so let's actually run this. Turn on the kernel. Let me start the kernel. Yes. All right. And okay, I import a bunch of stuff. Here is the egg carton function. Okay, and I'm going to plot the egg carton function, so you can see that. What am I calling it here? Okay, here's egg carton, and oh, there you go. Okay, there's the call to egg carton, and I'm setting the bounds. Okay, here it comes. All right, so this is the function. Okay, and the coloring is supposed to. Okay, so. The minima looks like is blue points, and the maxima are looks like these dark brown points. Okay, so this is the egg carton. Okay, and now we're going to do a heat map. Okay, the heat map is supposed to show you the local minima and the global minima using different algorithms. Okay, so let's see. We're plotting, and we're calling optimize, and these are the various algorithms, are the various types of gradient descent. Okay, so these are just the names of the algorithms, and we're going to call all the various algorithms and store the results in this dictionary. Okay, so DA is dual annealing, DE is differential evaluation or evolution, and BH is basin hopping, and I don't know what this one stands for. Now this one actually is interesting in that it finds all the local minima, not just the global ones. Okay, and so all right, so this plots a heat map. Okay, so that's what this function does. And here we're going to now look for the local and global minima and show them on the heat map. That's the idea. So here we are getting the results from calling these various optimized functions. And there is the plot, and it looks like this. Okay. And you know, I should have checked. Are we looking for minima or maxima? But yeah, as I said, the computations are the same. So whether you can convert a minima problem to a maxima problem. Okay, so then these are the various. Okay, let's say they're maxima. These are the global. Hang on, let's go to that web page. Maybe it says whether we're calculating minima or maxima. Okay. I just put these slides together the other day. So all right, so here is that. And okay, it's looking for minima. Okay, it's a minimization problem. And which makes sense because we've been doing descents. Okay, you can see that there's lots and lots of different algorithms here, and I just picked the ones that were the easiest to explain. Okay, so anyway, this one here, SGO Sobol, is giving us all the minima, and the marker is an X. Okay, and so. So okay, there you can see a couple of X's in here. Now this one, the red dots. Okay, marker plus. Okay, so here you can see the plus. Okay, so the different algorithms apparently are finding different points here. Okay, it could be that some of the minima are equal to each other, and so that they're finding different ones. So we have a blue disk, that's cyan here. Oh, MS is marker size. So we have a size 10 markers, and then we have these dots are size 8, and so here. This one is returning a list of all the minima, and that's what all these dots are. Okay, and then the others are think they're finding a global minima. Okay, and so okay, so here basin hopping, differential evolution, and dual annealing are these disks here. Okay, so there's a cyan one, a yellow one, and a white one. Okay, yeah, here they are. And then this algorithm is using these plus and X markers. Okay, and so we see the plus here. Oh, there's an X, and then this algorithm is also giving us a list of all the local minima, and that's what these dots are. Okay? Now, if we run this again, I believe that there is some randomness that it is going to look different. So that we run all the cells again. Okay, and get the last one, and see this one actually came down here. Okay? So I think there are different starting points whenever you run this, and so every run will give you a different result. Okay, here they are here, and then okay. So anyway, this is some code that is doing gradient descent, and I found this by so the Python page that basically has the description of this optimization function And you can see it has many, 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 many options. So apparently they lumped everything together into this one class, and then you specify which of the algorithms that you actually want. And so, and unfortunately, there are examples of the use of them, but not all of the examples actually have a nice image. So I picked the one that had the image. Okay. So you can see that this is a major topic, and I'm definitely not an expert in all of these algorithms. And maybe the next time I teach this class, I'll somehow find a way of spending at least an entire evening on these algorithms and not give you the condensed version. Okay? But at least now you know what optimization is all about. And then you've seen two major classes of algorithms, namely the Nelder-Mead and the gradient descent. And you also know what a gradient is, or at least what it tells you. Okay. All right. Any questions? I feel kind of guilty that I spent so little time on what is supposedly one of the pillars of data science. All right. Looks like I do have time to cover this last topic, which I probably should have covered it back when we were talking about regression. Is called logistic regression, and it's another thing that you may encounter. Okay, so logistic regression model use if the dependent variable, the y variable, has only two possible values. Okay, so for example, in the Titanic data set, okay, we knew what class the passenger was in, first class, second class, third class. And we also knew whether or not the patient survived, yes or no. And so there, for the survived attributes, it was either yes or no, okay? And so we could train a logistic model to predict based on the ticket class, whether or not the passenger survived, okay? So that would be a logistic regression model. All right, so here we go. And then you can see that, all right, here I'm bringing in the Titanic data set again, and survived. Okay, if we consider the class to be the independent variable, yes, 1, 2, or 3, right? And the dependent variable to be whether or not you survived, then that means that there are only two possible values for the dependent variable, yes or no. Okay. All right, so whoops, sorry. Okay, so then I convert the string first, second, and third to 1, 2, or 3. Okay, so then okay, and I convert yes or no to 1 or 0. Okay, that way I can deal with only numbers. Okay, so I basically converted this first column or this class column to a column of numbers 1, 2, or 3, and I've converted this column of yes or no to a column of ones and zeros. Okay, that's all this was. Okay, and then okay, I'm going to split the data into a training set and a testing set, right? The way we've done this before. Okay, so this is the machine learning version of doing regression. Okay, and then okay, so here is the data, and I've got I'm showing the first 10 rows of the training set. Okay, so you can see that the X values, the class is either 1, 2, or 3, and the Y value, which is the what we're trying to predict, is either 0 or 1. Okay, and then here's the testing set. Okay, and you can see that of all the rows, 981 of them ended up in the training set, and then 328 rows will be in the testing set. Okay. All right, here we are. We're going to do logistic regression. So of course, there's a Python function for doing that, and now we do we do the fit. Okay, and then after we've done the fit, which means we've done the training, we can use the model to make a prediction. Okay. All right. So we're going to compare the prediction of whether or not the passenger survived based on the passenger class, and we're going to then compare the prediction against the actual. Okay. And so here we are comparing the right decisions with the wrong decisions. And so it turns out we were nearly 70% accurate in training this logistic model, okay? Meaning that depending on what class you're in, 70% of the time, we will predict correctly whether or not you survive. Okay? And you know, in the beginning of the semester, we looked at the data, and sure enough, you know, if you're in third class, you probably will not survive, and if you're in first class, you probably will survive, and then the folks in second class were in between. Okay. All right, so this is a logistic model, and it uses what's known as the sigmoid function. Okay, and this is what it looks like. Okay, and so it says that for any data point, if the probability is less than a half, and so this function is giving you the probability. If it's less than a half, then it goes in one category, but if the function is greater than a half, then it goes into the other category. So that's the sigmoid function then tells you whether it's in one value or the other value of the dependent variable. Okay. All right, so that is in a very small nutshell the logistic function. Okay, and again, you would use this regression model if the dependent value variable has only two possible values. Okay, so it's almost like remember when we were doing probability, there was the binomial distribution where you know, the result was either yes or no, and then here is something similar, logistic regression, where you only have two values for the dependent variable. Okay. All right, so that man, I managed to squeeze that in too. I was worried that I would end up spending too much time on the optimization. I probably should have spent more time there, but no, that's it. Okay, so any questions about this? Yeah, sorry, it was kind of compressed, but I did want to make sure that you at least had an introduction to eigenvalues and eigenvectors, and also to optimization. Okay. Any questions? Okay, so I think the final exam, I believe, is a week from today. And the format will be similar to the midterm. Now the final is, I believe, nearly 3 hours. So well, it's the same amount of time that the class lasts, but I'll give you the full, I guess it's what, 2 hours and 45 minutes, something like that. I'll give you the full time, so that I won't try to give a lecture or anything during that time. And the format will be very similar to the midterm. There'll be some multiple choice questions and then some problems. And yes, I will not have any calculation problems in the multiple choice as I did last time. So all the calculations will be in the notebook problems. Okay? It will cover the entire semester with emphasis on the second half. Okay, so let's take a look at what did we do during the second half. Let's see, syllabus, there it is. Okay, so we had the midterm. Okay, so mostly it was statistics. Okay, we spent a lot of time on probability and some basic statistics in the beginning, and then we started getting into statistical analysis, and most of that ended up in the second half. And then we got in, and I gave you some examples of machine learning. Oops, my cat just jumped on the table here. Don't step on the keyboard, please. And then we got into linear algebra, okay? And then we ended up talking about eigenvalues and eigenvectors. See, I didn't even have optimization initially here, and we did include optimization. Where did I have linear regression? A logistic regression. I guess that was never on here either. Okay, so we'll emphasize the second half during the final exam. Okay, and it will be the same as the last time. Open book, open notes, open internet. You take it as two parts. There'll be the multiple choice parts that will be in the form of a quiz in Canvas, and then you also download a notebook that will have some problems in it. And during the exam, once again, turn on your cameras so I can stare at all your happy faces, and I can tell Dr. Chang that yes, indeed, I proctored the exam. Okay. There are some AI programs that supposedly do that proctoring, and some professors have tried using it, but it turns out that those AI programs have a lot of problems. Students say that, oh, I just looked up at the ceiling and the AI program claimed that I was cheating or something like that, or I leaned over and for an instant my face was not in camera view, and the AI program said I was cheating. So the AI program it really has a lot of problems, and I figure that, well, I can stare at you at least as well as any AI program. So we'll do it the same way as we did with the midterm. Okay. Any questions?
Yeah, Professor. I mean, it seems like 2 hours 15 minutes is the multiple choice questions will be less because the time has been considerably less compared to the midterm, right?
Well, I haven't put it together yet, so I don't know what percentage of the points will be multiple choice and what percentage will be of the problems. I have to come up with the problems first, and then depending on how many of them I come up with, then I'll decide how many multiple choice. The idea of the multiple choice, which of course is, in theory, but I doubt that it always works in practice. The idea of the multiple choice is that it tests whether or not you know something, and either you know the answer or you don't, and so you should be able to go boom 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 through the multiple choice. But I know that sometimes you stop and you look at the answers and say, gosh, which one is it, and you have to think about it. I would start with the problems, okay, because they'll be worth more points, and then allocate a certain amount of time. I don't know how much, but allocate a certain amount of time for the multiple choice. But don't start with the multiple choice and spend 2 hours on the multiple choice, and then you won't have time to do the problems. Okay. So that's how I would do it. But of course, I'm not the one taking the exam. Yeah. Now,
Our thing is like last time that 2.5 hours was very tight for us. So I was just asking because the 15 minutes has been reduced in the overall duration. So
oh, okay. I haven't looked to. Oh, okay. It says right here. Oh, okay. So it's 2 hours and 15 minutes. Oh, that's less time than the class, which was
Yeah.
2 hours and 45 minutes. Okay. Well, I will. You know, there's a rule of thumb, and you're going to laugh when I tell you the rule of thumb. The rule of thumb is that the instructor puts together the exam, and then the instructor takes his or her own exam and times how long it takes for the instructor to take the exam. And then you multiply that by 6, and that's how long you should give the students. So
okay.
that's the rule of thumb, and I don't think it works. So everybody will get the same exam, and if everybody only finishes, say, 2/3 of it, then then everybody will get a similar score. Okay, so but I'll try to make it reasonable, but
Okay,
it's really
thank you.
hard for me to predict what's reasonable.
Professor, will there be any Jupyter from the last semester for sample as you gave for midterm?
Yeah, let me look at that because it's not easy coming up with good problems, and sometimes I reuse them, and sometimes problems that were on homework from a previous semester will end up on an exam, and then vice versa. Some exam problems end up as homework problems, and so if I start giving out my problems, that limits what I have. And okay, I'll look and see what I have, and if I think it's appropriate, then I'll send out the old exam.
Okay, it will be helpful. Thank you.
Yeah. Okay.
Professor, I have one question. Will
Yeah.
there be any long question from the probability, or it's only after the midterm?
Well, I said that the exam will cover the entire semester, but I will emphasize the second half. And then, of course, a lot of the things we did in the second half built on what we did in the first half. And so we can't ignore everything that we did in the first half. Okay. But I think there'll be emphasis on linear algebra, because that was the major thing that we did in the second half.
There's a question in the chat regarding today's topic. Will there
Yes.
heavy emphasis on optimization on the final?
I'm not going to give you any optimization problems to solve. I may ask you some multiple choice questions to make sure you understood everything, but I'm not going to give you any. I am not going to give you any problems that you hadn't seen before on the homework. How's that?
Thank you.
All right. Okay. I do plan to take a break from teaching, so I will not be teaching at all in the fall. So and then maybe in next spring I'll start again. For the past 7 years, I've been teaching 5 classes a semester, sometimes 4. Like this semester, I only have 4, and over 200 students a semester. And boy, I really need to take a break. So I will not be teaching in the fall. Okay. However, I expect to continue being the PI for my grant to hire students for these internships at NASA. Now, I hope that by next fall, or maybe before the end of the summer, that the lockdown at Ames will be over, and there'll be a lot more internships, because right now the interns have to work from home, and because of security issues, not every job can be done from home by a student. And, so I hope to have more positions. And if the lockdown is over, you'll be able to actually work on campus. And being on the NASA campus is very, very cool. Okay, it's like being on MIT campus, where every building they're doing something. They're doing some really cool research, like, oh, that's the astrobiology building, and inside there are the astrobiologists who are looking for life on other planets, and then there are the people who are experts at rocketry, and so that they're there. People forget that the first A in NASA is aeronautics. So NASA is also very much involved with terrestrial, airplanes flying on Earth and airports, and so there's a lot of research going on there to make airports safer and to keep airplanes from crashing into each other. Now there's a lot of issues with drones. People are flying these drones everywhere, and you don't want airplanes running into them. And so there's a lot of research going on there. Okay, there was a data science intern 3 was a data science position. Recommender system. Remember when we were talking about natural language processing, that one of the functions there was to read a document and then find other similar documents. I think we did that with Shakespeare and some other, forget the other author. And so here, this was a data science position, and one of your classmates, not from this class, but from one of my previous classes, was hired. So that was great. So I hope to see more internships and maybe get some of you hired, because as you can see, many of these do not require US citizenship. As long as your visa, like an F1 visa, allows you to work in this country and US citizenship is not required, then you can apply. Okay, so the, I don't know if you know her, Nilam Shinde, okay, young woman from India, was hired for this position. Okay. And I will keep updating this as I find out more and more jobs. And then if you're looking for a full-time position, I have them here too. But each of these leads to the KBR website, and so you would apply for these directly, and I'm not really involved, other than I list the link, and so you click here to apply. Okay, but for the internships, I will look at all the resumes that I get, and then I forward the resumes to the appropriate hiring manager. Okay. And they do a pretty good job with these write-ups. They say what the job is about, what the skills are, and so forth. And then if your skills match, then and you're interested, then let me know. Okay. All
I have
right.
a quick question regarding
Yeah.
those internships, especially
Yeah.
like system-wide safety. I
Yeah.
think. So I noticed that they ask for a lot, right? Like C, C++, and Python.
Yeah.
Is this
I have told them that they ask for too much, which makes it really, really hard for students to dare to apply for any of these. So if you're good at Python, then you should apply. Okay, let's say that you're a super duper Python programmer, you're good with databases, and I don't know if you have any experience with embedded systems, then you should apply. Okay, the rest are are you interested in this? Do you have good communication skills? Of course you do. Now, this was rewritten. Originally, it was strong understanding of geographic information systems, GIS, and that was up here. And I told them, look, you're not going to find any student who can meet all those qualifications. And sure enough, I got 0 resumes for 3 weeks, did not get a single resume. So after they moved GIS down here, okay, so far I've gotten 1 resume, okay? But if you're at all interested in GIS, okay, what I was told was that if you get this job, they will teach you what you need to know about GIS. And the cool thing is that you're going to learn from GIS experts at NASA. Okay? So if you think you meet most of the qualifications, then you should consider applying. Because I doubt that they're going to find any student that meets all the qualifications. Okay, and this grant, in order for me to win the grant, I had to agree to allow students from other universities to apply for these positions. And if a student from another university is chosen, then my grant will pay for it. Okay, so I had to agree that I could not limit my grant money to just San Jose State students. But I think you're getting the first shot at these, because as soon as I find out, I publish it. And then I send out a message to all my students saying, hey, look, I just published this. And so I think I'm giving San Jose State students a first shot. Now, I don't know how students from other universities are finding out about these. They may be periodically checking the KBR website, because they're also published by KBR. KBR is the primary contractor, and San Jose State is the subcontractor. Okay, so that's the way it works. So other students from other universities, I would assume, are periodically checking the KBR jobs website, whereas I am directly told about these positions, and then I immediately push it out to our students. So hopefully I'm giving our students at least a slight advantage. Of the students we've hired so far, and we haven't hired that many because there just haven't been that many internships. I think we've hired 6 students so far, and 2 of them are San Jose State students. A third of them are being taken by San Jose State students. Okay, but we're competing against students from many other universities. I hope that we should have like a dozen or more students working at a time. I did this 2 summers ago with a smaller grant, and I had, I think, a dozen students working during the summer. And of the 6 students I've hired, they were hired for last summer, and they've already finished. So I only have very few students currently working at Ames, and I hope to have an army of students there. But we have to make sure that our students get hired. Okay. All right. Any other questions or comments?
Quick question about the final.
Yeah.
Just confirm with you that first, is the time really 5:30 to 7:15?
It's whatever it says.
Okay.
That is published by, that's a time determined by the university, and they try to work it out so that no 2 classes will have finals at the same time. It doesn't always work, but they do a pretty decent job of it, and so these are the times that that 5:15 to 7:30. Okay, let me show you. There is a web page, final exam. There we go. And so here it is. And we are a Thursday class, so that's a group 2 class. Okay, Thursday, that's R, and we start at 6 o'clock, and so let's see, 6 o'clock, and does that match up what I said? Okay. Let's see, something 6 o'clock is down here. Okay, so it's o'clock. Yeah, it's yeah. Looks like it's 5:15 to 7:30. Okay, and the class is a Thursday class, so it's Thursday, May 20th. Okay, so I can't change that. If I change it, it's going to cause problems with some students who may have other exams. Yeah. Okay. Any other questions? Okay. Well, you're lucky it's not 5:15 in the morning because, well, okay, yeah, there are some exams that start at 7:15 in the morning, and we don't have that problem. Okay. All right. Any other questions?
Professor,
Yeah.
all the existing assignment gradings will be done in the.
Oh, okay. I will talk to the grader and see when he'll get everything finished grading. I may have to jump in and help him grade, so that at least you'll have all the you'll know what your scores are. Of course, I've given you my answers, but you may want to find out if the way you did it was also considered good. Okay, I will pester him and make sure he finishes grading everything.
Okay. Other question is, this Zoom recording is going to be there for some more time after the sessions complete, or it will be removed?
Well, so these class recordings will probably be around through the summer, and then I don't know what happens after that, because since I'm not teaching next fall, I don't know if they'll even let me keep the. I mean, I may lose contact with Canvas, and my website is on a school server, so I don't know if I'll still have access to the school server, although I can probably move everything to a different host. But yeah, I don't know what's going to happen at the end of summer.
Okay.
Yeah, because I said I was going to take a half-year break, and hopefully the university will not erase everything that I've done, but they may. They say, well, you're gone. We're going to erase everything. You start all over again if you come back, and if that happens, then well, I'm going to back up everything for sure. Okay. Any other questions? Okay. All right. Well, I hope you all had a good time. And there are these surveys you're supposed to be taking. These SOAPs. You evaluate the class and the instructor. So be sure to do that, okay? Because they use that to determine, gosh, you hire Ron back because the students all hated him, so let's not hire him back, or whatever. So be sure you do that for all your instructors. Okay. All right. No more questions. If you do have more questions, then I will monitor the discussion forum, and I can answer questions there. Okay. All right. Then I will sign off, and all these chat messages. Okay, I think I answered all the questions. All right. Thank you for coming. And I am ending the meeting.